Hello, welcome to this lecture on Pohlhausen method, which is an approximate method for the solution of boundary layer and boundary layer over solid walls. Boundary layer when the fluid flow over solid walls. So it starts with the Von-Karman momentum integral equation, which is obtained by integrating the Prandtl boundary layer equation over the height of the boundary layer at any particular value of x, and we get the equation as d by dx of u squared delta 2, and capital U is the potential flow velocity, delta 2 is the momentum thickness, plus u du by dx. Delta 1 is the displacement thickness. The wall shear stress is represented by tau naught at y equal to 0. Wall shear stress, the shear stress at y is equal to 0 by rho. So this is the equation which is called the Von-Karman momentum integral equation, and this product differentiation, if you do, you get u squared d delta 2 by dx plus u dou u by dou x is common here also. Then there will be 2u will be there. So there is a 2 delta 2 plus delta 1 is equal to tau 0 by rho. So this is an expanded, the product differentiation expanded equation of the momentum integral, Von-Karman momentum integral equation. And if you look at the dimension of the terms of this, this tau naught by rho, it is of the unit meter squared per second squared. So Newton per meter squared, kg per meter cube. So Newton is kg meter per second squared. So kg cancels. This meter cube into meter is meter squared. So every term will have a unit of meter squared per second squared. The first thing Pohlhausen did was to non-dimensionalize the equation. So to non-dimensionalize the equation, we also know that suppose we have the momentum thickness delta 2 by nu, this is nu is kinematic viscosity. So meter divided by meter square per second in the meter by second. So this meter and meter cancels. So this is having a 1 by meter squared per second squared, or 1 by velocity squared. So if you multiply each and every term of this equation by delta 2 by nu u, that's how he has non-dimensionalized the terms, or dimensionless terms are the equation with the dimensionless terms are obtained by multiplying the equation by this term. So by that you get this u squared and one u is there, so we have u delta 2 by nu d delta 2 by dx is going to be here, plus this one u and one u cancels, so there will be a delta 2, there's a delta 2. So then du by dx, there is one nu is there, so one multiplying that, so there is a one nu is there on the denominator, there is a nu, there's a denominator on nu, so that completes that. Then there is a u cancels, so 2 delta 2 plus delta 1 is equal to tau 0 by rho, delta 2 by nu u. So So that's how we get. Now it is non-dimensionalized. So this delta 2 can be taken outside. So this delta 2 squared will come, and this delta 2 will go. By that, there will be a delta 2 over here. There is a delta 2 over here. So delta 2, okay. So this can be written as again, so this delta 1 by delta 2 is there, and this delta 2 divided by delta 1 squared, there is a delta 1 squared. So this way, this equation is rearranged to write an equation in this form. So again, what simply, okay, now it is all the terms are dimensionless. So now again, this delta 2 can be taken inside the differential, and nu also can be taken inside the differential, assuming that the viscosity does not change within the boundary layer. So that is normally the case. Normally in boundary layer flows, okay, especially incompressible boundary layer flows, the kinematic viscosity of the fluid is assumed to be constant. So that with that assumption, we can write this U is there, then half into d delta squared by nu d by dx of delta squared by nu, plus this is written as delta 2 by delta, not delta 1, and maybe this multiplication is with the correct, with the bound layer thickness, not displacement thickness delta 1. So this is also not delta 1 but delta, and this is also with delta. So delta 2 by delta, the whole squared, into du by dx into delta squared by nu 2 plus delta 1 by delta 2 is equal to tau naught by rho delta 2 by nu u, and the whole term of this is dimensionless. This is dimensionless, this is dimensionless, this is delta 2 by delta is also a distance ratio, that is dimensionless. So this is also dimensionless. So this is a dimensionless. So in Pohlhausen method, this is related to the potential flow velocity gradient, which is related to the pressure gradient the bound layer is subjected to, and this is denoted by a lambda. So du by dx delta squared by nu is denoted as lambda, and this is a delta squared by nu. If you look at it, it has a dimension of this meter squared by meter squared by second. So it is going to be a dimension of time dimension, or a second unit having unit second. So it is denoted by z. So this how the Von-Karman momentum integral equation is rearranged for the Pohlhausen method. The primary aim is to make all the terms dimensionless and also to introduce some new variables. And actually, this is said, and this lambda are the variables that is going to control the boundary layer parameters. So in that way, it is arranged. So we are having u by 2 d by dx of z. What is z is delta 2 squared by nu plus delta 2 by delta the whole squared. Then there is a lambda, and then 2 plus delta 1 by delta 2 is there, is equal to tau naught delta 2 by u into nu. So this kind of an equation, tau naught by rho is there. So this is the kind of equation we are having, in which z is equal to this, and lambda is equal to delta squared by nu dou u by dou x, where u is the potential flow velocity, is that. So Okay, so further, okay, now, okay, this is there and this is there, the z is there. So if you have a division, divide these equations. So z by lambda is equal to delta 2 by delta the whole squared into 1 by du by dx, or 1 by u dash, or okay, you can write u dash z is equal to lambda into delta 2 by delta the whole square. So I have this u dash is the velocity gradient, potential flow velocity gradient, and this is again rearranged. This equation is again rearranged to write. So I will copy this. So this is again rearranged to write dz by d. So I have having dz by dx is equal to 2 by u whole into tau 0 by rho u nu delta 2 minus delta 2 by delta the whole squared lambda 2 plus delta 1 by delta 2 is the kind of equation. So, and another equation is u dash is z. So u dash is z is equal to lambda into delta 2 by delta the whole square. So this is one equation, and this is another equation. And this is these are the two equations, important equations, which are going to be solved, numerically solved. This is an equation for dz by dx, which is solved by numerically over the body surface, starting from the forward stagnation point on the body, and this equation and this equation are solved for the different parameters, starting with a certain set of values. The solution, numerical solution, is done to find out z. So we have to find out z lambda. Once z and lambda are known, we will be able to find out all the other relevant boundary layer parameters. So that is what is done in the Pohlhausen's method. So now, for this method to work, we have to obtain the equations for, the delta 2 by delta, which is the ratio of momentum thickness to boundary layer thickness, delta 1 by delta 2, and tau 0 divided by that is mu u delta 2 into delta 2. All these things we have to obtain the equations. So for that, okay, these are those equations. Just the 2 is multiplied to inside to write this equation. Here, one more adjustment is done, and to write that this is tau 0 delta is there, tau 0 delta is there, so it is made delta, so that this is delta 2 by delta is made. So that way there is a minor adjustment of further minor adjustment that is there into delta 2 by delta. So that way it is arranged, and that equation is there. That is this equation. This is the second equation. He said u dash is du by dx. These equations 1 and 2 are numerically solved to obtain z and lambda for the boundary layer over the body. For that, another prerequisite is the an approximate velocity variation over the boundary layer. So we have the boundary layer. Over a body surface. So this is the body surface. This is the body surface. This is the body surface. This is a bound layer. Okay, slightly not correct. Okay, it's okay. So it is a velocity. So this is the velocity, potential velocity. From there onwards, it is like that. So here we are having no slip. U is equal to 0, V is equal to 0. So we take a variation, approximate polynomial variation for this velocity profile in the bound layer. By satisfying U is equal to 0, we can write A eta plus B eta squared plus C eta Q plus D eta raised to 4 is a fourth degree polynomial which satisfies the condition U is equal to 0 at Y is equal to 0 at Y is equal to 0. Here it is written as a function of eta. Eta is equal to Y by delta, which is the Y is the vertical distance along the normal direction, and delta is a function of X. So Y by delta. So at Y is equal to 0 means eta equal to 0. At eta equal to 0, if you substitute U is equal to 0, you will get that kind of a profile is taken, for which you can write dou u by dou y as like this. Dou u by dou y is like this. Dou squared u by dou y squared is this. So, and the boundary conditions are on the wall surface. On the wall surface here, on the wall surface here, that is at y is equal to 0, if we have the Prandtl boundary equation, u dou u by dou x plus b dou u by dou y is equal to capital U du by dx plus nu into dou squared u by dou y squared, and on the wall u is equal to 0, v is equal to 0. So there is a velocity gradient, potential velocity gradient, and this is at y is equal to 0. So at y is equal to 0, nu into dou squared u by dou y squared is equal to minus u into du by dx. Okay, that condition when you apply, that is at y is equal to 0 also means eta is equal to 0. At eta is equal to 0, theta equal to 0 means d squared u by dy squared. So this is nu into this u by delta squared into 2b, and put the eta equal to 0. This is equal to minus u du by dx, minus u du by dx, and this delta squared is taken to this numerator. Delta squared is taken to this numerator, and nu is taken to this denominator, denominator, and this u and this u and this u and this u cancels, so we get b is equal to minus 1 by 2 delta squared by nu du by dx. So we get b is equal to minus 1 by 2 delta squared by nu into du by dx, and we have earlier taken this as lambda. This is exactly equal to lambda. So b is equal to minus lambda by 2. We get one of the coefficient b is equal to minus lambda by 2. And other things, now we are having three more conditions at y is equal to delta, that is at the edge of the boundary layer. Y is equal to delta. Y is equal to delta means eta is equal to 1. We have u by u is equal to 1. Dou u by dou y is equal to 0. Dou squared u by dou y squared is equal to 0. And that can be, so at eta equal to 1, u by u is equal to 1. That gives you a plus b plus c plus d, another one equation. And this dou u by dou y equal to 0, that means eta equal to 0, eta equal to 1, that is a plus 2b plus 3c plus 4d equal to 0. And dou squared u by dou y squared is also 0 at the edge of the bound layer, or eta equal to 1. You get 2b plus 6c plus 12d equal to 0. And these are three equations, plus this one can be arranged in matrix form like this. So this is a plus b plus c plus d is equal to 1, and b is equal to minus lambda by 2. These things are arranged in the matrix form, and solving a b c d, we get a is equal to this, b is equal to this, c like d like that. So a has a constant part and a part that depending upon the pressure gradient parameter lambda. So writing that polynomial back in the form that is initially proposed, you get u by u is equal to some part which is constant and functions of eta, and something part which depends upon the value of lambda. So this function is written as capital F eta, and this portion is written as capital D eta. So we have F eta and D eta are the functions. Now that we calculate the displacement thickness delta 1, you know the fundamental equation is 0 to delta 1 minus u by capital U dy, and we are using eta is equal to y by delta. So dy is equal to delta into d eta, and this dy is made into delta into d eta, and when y is equal to delta, eta becomes equal to 1, the numerator, the upper limit becomes equal to 1, and this delta is taken back here. So delta 1 by delta is integral 0 to 1 minus u by u is this function. So, and we have this expression for this and this, and integration we get this one as a ratio of delta 1 by delta, and you can see that there is a constant part and it's a function of lambda. Delta 2 by delta is u by u into 1 minus u by u dy over integral 0 to y is equal to 0 to delta, and that also that the variable change will make a delta 2 by delta, and limit becomes this one, and this u by u plus into 1 minus u by u, and that upon integration will give to this kind of an expression, which is also a function of lambda. And tau 0 is equal to mu into dou u by dou y is equal to 0, and dou u by dou y expression here it is there, dou u by dou y expression, and that is the expression, and y is equal to 0 means eta is equal to 0, so it will give it to ua by delta. So that ua by delta is substituted to ua by delta, and mu u by delta, and av is the coefficient which is unknown coefficient determined as 2 plus lambda by 6. So that way you get tau 0 delta by mu u is equal to 2 plus lambda by 6. This is dimensionless. This is a dimensionless wall shear stress. And as per this equation, the dimensionless dimensionless wall shear stress becomes equal to 0 when lambda is equal to minus 12. Substitute minus 12, that becomes equal to 0. And when lambda reaches on the body surface, when the value of lambda reaches minus 12, the shear stress becomes equal to 0, and at that point on the wall, the velocity distribution will be like this. That is the velocity. This is the velocity variation. The tangent will be along the y-axis, so that dou u by dou y is equal to 0 there, and that is corresponding to this x. This x corresponds to lambda of that particular x is minus 12, and beyond that point, the boundary layer no longer be attached to the wall. There will be a separation. So we can find that there's a reverse flow here. So the boundary layer happens. This actually happens due to the lambda exceeding. That the lambda is the pressure gradient parameter. The adverse pressure gradient increases beyond a certain value. When there is no adverse pressure gradient for the flow, that depends upon the potential velocity distribution. When that kind of situation is not there, this situation will not arise, and the lambda will be always less than minus 12. But if in a particular case, because of the pressure gradient, if lambda becomes equal to minus 12, the flow separates. The phenomena is called flow separation. So the Pohlhausen method can find out at what point on the solid wall boundary layer the fluid separates. Until that point, what are the values of lambda, what is the value of z, by which what is delta 2, etc. can be obtained. So these are our fundamental equations which is derived, and this is also another equation. Okay, now what happens is that so as far as this equation is concerned, so the whole of this we found that is a function of So 2 plus lambda by 6 is there, plus tau 0 delta by nu u. This entire thing multiplied by, so that is 2 plus lambda by 6 into 2, and that is this term. Delta 2 by delta is a function of lambda. We have found this is a function of lambda, this is a function of lambda, this is a function of lambda, and this delta 1 by delta is a function of lambda, this everything, this is lambda. So the everything here is a function of lambda, non-linear function of lambda, which we are writing it as f1 of lambda by u. And the other equation is z du by dx is also lambda into delta by delta is also function of some function of lambda. So that we are having, that is the square of this entire thing square will be that, so that it is totally a function of lambda z into du by dx. Now that these equations 14 and 15 are solved on the body surface, starting from the forward stagnation point. Suppose we are having a body, a solid body like this, a solid body like this we are having, flow over a solid body, and we take our x is equal to 0 at this point. We take x is equal to 0 at this point, which is the forward stagnation point, and the x varies along the body surface. X varies like this. So this length of the body is divided into discretized for the numerical solution, like points 0, 1, 2, 3, 4, 5, and out of which at the zeroth point is the stagnation point where u is equal to 0. So u0 is equal to 0. The denominator is equal to 0. So f1 of lambda 0 by u0 is equal to 0. Though, so to have a finite value for dou dz by dx at x is equal to 0, where u0 is equal to 0, this numerator also must be equal to 0. So we start with a value of lambda 0 such that f1 of lambda 0 is equal to 0, or we choose a value as lambda 0, which is a 0 of the function f1 of lambda. So if we have the lambda along the x-axis and y-axis along f1 of lambda, if we plot the variation, so it will be something like this. So we'll have the zeros like this. So then it will go like this. So this kind of a variation we have. So this lambda 0 can be found out by drawing this or by solving this equation by some kind of nonlinear solution of equations like Newton-Raphson or such. So we get the lambda at x is equal to 0 or lambda 0. Lambda 0 is equal to 7.0523. That is the value you get. And consequently, so there's a 0 by 0 form is there for this at this 0 by 0 form is there. So there is a 0 by 0 form is there at x is equal to 0. dz is f1 lambda 0 by u0 as a 0 by 0 form. So what we have to do is we have to find out the limit by using L-Hospital. It can be done by using L-Hospital rules, and some working out of that will give a solution for dz by dx by application of L-Hospital's rule. We get it as at x is equal to 0 as this kind of a relation we get, which consists of the second derivative of the potential flow velocity at x is equal to 0. And so z at x is equal to 0 is for that lambda f2 of lambda 0 by u dash at x is equal to 0, or u dash 0. So that is the velocity. U is not, so there is no point, there is no difficulty in finding out u dash 0. So this kind of a value get. So that is from the velocity distribution you get. So at the starting point we have z0 and dz by dx at x is equal to 0. So z0 is there, then lambda 0 is there, then lambda 0, z0 we know z0 lambda 0. So lambda 0 is there, z0 is known from this one. So it is known in this particular order. We know lambda 0, So we know lambda 0, hence z0, and dz by dx at x is equal to 0. And these are the starting values. So dz by dx for any ith point can be discretized as zi plus 1 by minus zi by the step length h is equal to f1 of lambda I divided by u of I. So for f1 of lambda I, by knowing lambda I, and this is an input, by knowing it by zi we can progress to find out zi plus 1 by this kind of a numerical scheme. So once zi plus 1 is known, once we have zi plus 1, zi plus 1 is known. So when that zi plus 1 is known, yeah, zi plus 1 is known, we know for any point by use this equation, we use this equation. This equation is taken, this equation is taken, zi plus 1 and du by dx at I plus 1. So this is an input for the calculation. This is just now obtained. This is equal to f2 of lambda of that I plus 1 we can write. And lambda I plus 1 is not known, this is known, this is known. So f2 of lambda is known by this value. This is a nonlinear function. This is solved by Newton-Raphson method to get lambda I plus 1. So thereby we progress the solution by knowing lambda 0, z0, dz by dx at x is equal to 0. We can solve lambda 1, z1, dz by dx at 1, and so on to find out the values of all the parameters. We know any zi is equal to delta 2 squared by nu. By knowing nu, you can get, by knowing zi, okay, delta 2 squared at that point I, at that particular point I, and we can find out delta 2 at that I, at that point I. Once we have delta 2, we know the ratio delta 2 by delta is some function of lambda, and the lambda I is known. This can be evaluated. By knowing delta 2, we can get the boundary layer thickness. Now, by once boundary layer thickness is known, delta 1 by delta, we have another psi of lambda that is there. So by knowing delta, we can get delta 1, and we have all the also 2 plus gamma by 6 as the dimensionless wall shear stress. From that we can get wall shear stress and the skin friction coefficient. All the relevant parameters we can find out by using the method. Only thing is that it's an approximate method. A slight variation from exact solution will be there. There are methods, there are people who have solved the boundary layer by using other methods. There will be comparatively, but it can be acceptable as an engineering solution. And this is some portion of the computer program written in FORTRAN for the purpose of yes, determining the boundary layer over a cylinder, for which dz by dx is equal to 0. Other things remains same as that, and that is solved by doing this. And so this is the subroutine. AL value is the subroutine that solves the value of lambda from f2 by using Newton-Raphson method. This is the major subroutine, or the is the one subroutine which requires some kind of a coding. That is the coding is for Newton-Raphson method. Otherwise, it's a very simple code. This code will give you lambda is equal to minus 12 at angle theta of something like 107 degree. So the boundary layer can be solved up to that angle 0 if we measure somewhere here, somewhere here, somewhere here in the flow separate. So this angle is 107 degree. Yet that is close to the values obtained by using other methods. So I'll stop for now with this.